Agora que a água e o café chegaram, nós podemos começar. Bom dia a todos. Hoje eu tenho o enorme de introduzir o pesquisador que diretamente catalisou a realização da 7ª ESSO. O Timothy BROCKSOM, ele possui graduação em Química pela Universidade de Liverpool, em 1964 e 1965, e doutorado em Química Orgânica pela Universidade de Liverpool. Ele finalizou o seu doutorado em 1968. Bom, ele realizou 2 estágios de pós-doutoramento. O primeiro na Universidade de Stanford, nos Estados Unidos, de 1968 a 1970, e o segundo na Universidade de British Columbia, Canadá, de 1971 a 1972. Em 1985, o professor Timothy tornou-se livre docente pela Universidade de São Paulo. Atualmente, ele é professor titular da Universidade Federal de São Carlos. Ele tem vasta experiência em síntese orgânica, desenvolvendo síntese enantio e diastério seletivas de terpenos bioativos. Bom, ele usou, então, para essas sínteses monoterpenos que são abundantes na natureza, e ele tem desenvolvido métodos sintéticos de carbociclização e oxociclização, especialmente cicloadições 2+2, 3+2 e 4+2. Várias metodologias foram desenvolvidas em seu laboratório, tá? Reações mediadas por complexos de metais de transição, inclusive metástase de fechamento de anel, reações Alder-Eno, anelações e fragmentações, ciclopropanações e reações de expansão de anéis, entre outras, tá? As pesquisas realizadas pelo professor Tim BROCKSOM renderam aproximadamente 50 dissertações de mestrado e tese de doutorado, bem como aproximadamente 70 publicações em revistas de alto índice de impacto. Bom, além de vários capítulos de livros. Para concluir esse resumo de um currículo muito amplo, vale mencionar que o professor Timothy BROCKSOM é um dos precursores da síntese orgânica no Brasil. A importância dele para a síntese orgânica é sem tamanho. O minicurso que vocês terão hoje é um minicurso sobre síntese orgânica, e eu tenho certeza que vocês ficarão abismados e será algo inesquecível. Professor Timothy, a palavra é sua. Muito obrigado.
Well, good morning. Okay, great. I was going to talk in Portuguese, but we've just been discussing here. If there's no problem, I think I'll just try and speak English. It's been such a long time since I had a chance to speak English, because I always speak Portuguese all day long. So we'll see how it goes. So what we're going to do today. Let me. Now, this is a publication which we presented. You can see myself, Andre, Leandro, and Kleber. We wrote this review about the new directions in organic synthesis, because we have noticed that up to the end of the last century, we did organic synthesis in a certain way. And as we will perhaps try to show you, perhaps not the best way. Now, organic synthesis has changed quite a lot in every possible way. Ideas, concepts, the way of doing things. And I want you to bring up to date. Most of the reference I will use are actually after 2015, so it's an update on this story. Okay? And that's what my objective is today. Well, we start off usually by that chemistry is the central science. You can see quite clearly chemistry is here, and all the other basic sciences are derived from chemistry. We have an interesting comment from a famous medic. He got the Nobel Prize a long time ago. He's called Kornberg. And he says the only way that the sciences can communicate is by talking chemistry, because we work with molecules, and everybody works with molecules. So this is not just on chemistry being the central science. And that means you can get lots of jobs, which is a very important thing to all of us to think. If you're going to do chemistry, don't forget sometime afterwards you will have to do jobs. So, what I want to do now is to give a brief introduction to methodology and organic synthesis. A little bit of what, a little bit of why, and a little bit of, and then we'll go into some more details and work out. I will then get to show you some very recent syntheses which are going of where organic synthesis should be going. And I'll make the comment now. You'll see things about organic synthesis, perhaps academic. And then you'll say, well, that's funny. Simon said the same thing on Monday. Hans-Jürgen said the same thing yesterday. But they have spent most of their lives in the pharmaceutical industry. So perhaps the two kinds of syntheses are getting very close to each other. We are going towards the industrial pharmaceutical viewpoint, and to some extent they're coming in our direction as well. That's the basic idea I want to try and get you to understand. First of all, this is really just a simple at the bottom here. When you said synthesis, synthesis, that's not true anymore. All chemists and other scientists do synthesis. You do inorganic synthesis, nanomaterial synthesis. Everything has to be made by synthesis. So we have basically the message at the bottom. Synthesis now is making any kind of material. Okay? This is just this was meeting. You can see obviously we're in Rio de Janeiro. You can see certain things, and that person there is also thinking about organic synthesis. So it's everywhere and in our imagination. Now this is a article by Philip Ball, which is in Nature, 2013. And he's not an organic chemist, he's just a general writer, but he wrote a really interesting article on why should we synthesize. So we start off with why synthesize. Now I'm just going to show from this article. There are 2 points he makes. One, synthesize, and he makes this very important, that seems obvious, but perhaps we weren't doing that before, and now we are trying to do this. That's the big idea. of course, why do chemists make molecules? Because that's the obvious reply. Molecules for our society, not just of obviously the pharmaceutical industry, but all kinds of interests. And I also put this point up here. This is the new into the machine, and the comes out here, and that's the basic idea we're trying to get towards. There are some people already, as really exists. Okay. It's run. It's on. I said England. I should remind to say. Oops. Sorry about that. I always and we say in Portuguese, Reino. Okay, so we're not too sure whether it's really united or not. Anyway, this project you might want to look at later on. The idea is this: you dial a molecule. You pick the telephone up and say to the people in the project, I want this molecule. And they will make it for you or tell you how to do it. And this is a big project underway in England. Why do we need to make molecules? Because they're the here. The chemical abstracts register every new molecule with a distinct number. It can be a molecule, material, doesn't really matter, any kind of since 1965. There are some before, but basic 65. But the most amazing thing is that this number is doubling every 4 to 5 years. In other words, it'll be in 300 million in about 3 or 4 years. And that's an amazing signal of we are really synthesizing a lot. Well, what should we synthesize? Well, first of all, bioactive natural products, future drugs, and fine chemicals for a modern society. With the wonderful comment from this Scottish gentleman here about 100 years ago about what are organic compounds. Okay. What should we synthesize? Well, to be honest, our field is much, much bigger than I put on the last slide. If you look at this slide, you will find, oops, sorry. There we go. There's the heavy chemical industries. You can see they're basically, and then of course now we have the biomass industries. Perhaps you can think of industries here, and I put it a list. There are other industries. You could recognize agrochemicals and pharmaceuticals as being the obvious members of this group, but you go down, you can see flavors, fragrances, cosmetics, treatment of water, food and feed ingredients, and also of course beers, wines and drinks. It's a chemical industry. Okay, so, and the biomass industries, which I've always thought about as being, for instance, what Chris told you before. We work with monoterpenes as starting materials, and they're from the biomass. And it's an amazing quantity of compounds. Next question. We've gone through why, we've gone through what, and let's see now how can we synthesize organic compounds. So what did I do here? I looked first of all at academic syntheses. And what we look at here, we choose the right molecule. Singular, one molecule. And then we try to do this synthesis in the so-called originality. We all look for the so-called elegance. I have the faintest idea what elegance is, really. Perhaps somebody might explain to me. But every about somebody says that everything's being done elegantly. I still haven't worked out what it is. But anyway, it's by part of the art. There's the art, and you use the key reactions for new industrial syntheses. You have to choose the right molecules. And then you have to do this with efficiency, time, looking at costs and prices, and of course the ones for a new. We'll be seeing a little bit of all these two aspects later on. Just don't synthesize a natural product recently published without making sure they got the structure right. There are many examples where the structure wasn't right, and the main author here, I think you get a little bit upset about making molecules and find that they didn't correspond to the compound that had been isolated. So this example, the bottom, diazonamide, this is a very interesting example. The X-ray got it wrong, so you can't even believe X-rays. Absolutely. If you want to just check, I'll just point out what we do have. Oops, sorry, I haven't really got used to this yet. We'll get there. We have nitrogen and we have oxygen. This is the X-ray structure, wrong, and this is the right structure, proved by synthesis. If we hadn't done this, if somebody hadn't done the synthesis, we'd still be believing the right. So we have an exchange of nitrogen, oxygen, and to correspond, the oxygen and nitrogen have been changed. In other words, X-ray doesn't really distinguish between oxygen and nitrogen atoms. So this is a warning. Okay? Well, this is a nice example of where art comes into organic synthesis. Many of us think about using Lego building blocks. So we've got a sample of Lego building blocks, and we use these building blocks, which we can buy, and we get them to all come together, and we make bigger and more complex molecules. So where does this come in here? This is our synthetic target. Mona Lisa was made from Lego. Okay? That's not possible. But whatever image, it was quite clear that this here is made from Lego. So you could use Lego building blocks to make anything. Okay? Oh, how can we synthesize? That's the big question. We've heard quite a lot Monday and yesterday from the two colleagues about how can we synthesize. First, I recommend that you do a analysis of the molecular structure. I'll show the next slide what that really means. Ring systems and stereochemistries, functional groups, stereochemistries, difficult to make. You want to look in the molecule to see if you can see some subunit. And I can monoterpenes. So I say, well, this part here is my monoterpene. I will just get my monoterpene into the bigger terpene. That's the one way. And obviously examine the molecular structure. Here's an example. Giving credit, Ursula was the person that made this slide for me. We are looking at longitudinal on retrostatic analysis. This was published in '64, Jacques, of course, and here's longifolding. That is the usual way to write it. What Ursula did was to flip it around, until she came back to longifolding. Now, if you look at the structures, you might have Well, they are and that's the whole idea. You must look at the compound from all possible angles, because every distinct view of the molecule will give you a different reply. When I look at this, sorry about this, when you look at this molecule, you see certain ways of making it. When you flip it over, you can see perhaps a different way of making the molecule. And that is the idea, to give you choices and options about how to do synthesis. The more you see, looking from the back side, the front side, the left side, the right side, gives you different on how to synthesize this molecule. Now, Dirk Trauner recently published this interesting article, which he calls The Chemist and the Architect. It's a nice thing to look at. It reminds us that we are constructing molecules, and if we do it correctly, we are corresponding to architects and engineers. And he showed us morphine, but he did the same thing. He flipped it over, and now you can see, looking at morphine, how many different ways you can think of synthesizing morphine, many of which haven't been done yet. Some have been done, but this will think about synthesis. Well, the next thing is, how do we do it? We call it retrosynthetic analysis and disconnection. So what we do is, in this, sorry about this once again, I think I've got a big thumb and small buttons, so I have to hold the time. Here we go. The best way to do the process is what officially Corey published in '64, then published a wonderful book. And what he does is to look at the structure, let's say longifolium, morphine, and by way of bond disconnections, we can get, in the inverse chemistry sense, we can get down to simple molecules. Here's a nice idea. You must use real reactions, known or unknown. How can you use an unknown real reaction? It's easy. You plan it, and then you start to make the new reaction. And what we all need today are new reactions. As we will see, most of our reactions are very old. So, you can do it on paper yourselves. You can do it with a computer. The computer obviously is better, quicker, and everything else. It has one tremendous problem. It can't create anything which wasn't put in there. And it can't think of a new way of doing something. So the computer is wonderful to help you, but don't depend on the computer. If you use the computer, your synthesis won't be very original, and probably they'll be like somebody else has already done. So we have three people here. We have Corey, the inventor. Perhaps not the inventor, but we all give him the credit for inventing. We have Stuart Warren, who teaches us how to do all this. And finally we have Grabowski, who has now made the retrosynthetic analysis without any effort whatsoever. The thing is so good that Merck Sigma has bought his program. It used to be called Chematica, and now it's called Cynthia. So you can buy the program and use the program to make. This is more or less parallel to what Hans said yesterday about your program. So there's a bit of competition now on the point. Go on, please tell everybody. Is it well, this is not free, obviously. So now, these are the kind of things which we try and students seem to think that organic chemistry started in 2010, and one of the last 9 years are worth looking at. And people forget last century, even the century before. We will see that many modern syntheses use reactions which come from 18 something, 18, not 19, I'll be showing you some reactions if we get time, and after she get there. So here is the Robert Robinson, the most famous organic chemistry of the first half of the last century. The second half we will say it was Woodward, but first half we will say it's Robert Robinson. And just to remind you, the building where I did my PhD is called Robert Robinson Labs. He really was very popular in Liverpool. 1917, he synthesized an alkaloid, and as you can see, it is very symmetrical. And he observed that, and you can see how we used to write structures a long time ago when we didn't have ChemWord, ChemDraw, and all these kind of things. It was done by hand. So, looking at tropinone. And what are these things here? To me, they are disconnections. He invented disconnections well before Corey. I won't suggest that Corey didn't see this, maybe he didn't. But I'm concerned that analysis and disconnection certainly was Robinson. So, there we go. And this is the best organic synthesis of all times. Why? Because it's or perhaps bio-inspired, as you put. It's done basically in one step. It's a multi-component reaction based on the Manic reaction, and the yield is about 40%. This is considered by Paul Wender the ideal synthesis, if it wasn't for the low yield. We wanted 100% yield. We only got 40. Anyway, so the sequence, you mix in succindialdehyde, methylamine, and when it's all started to react, you put in this acid. The reaction goes alone, you just leave it, then you get out of it tropinone, a little bit of CO2, and this, for anybody who does not understand, that is calcium. That was the way we used to write calcium a long time ago. Why is the yield about 40, and why is it so low? Well, I don't think it's low, personally, but why is it uncertain? Because these compounds, this was more or less available. This compound you have to commercial in 1917. It's actually, and when you make it, you're not really sure what the purity is in 1917. So you're not really sure if you are using 100%, so the weight doesn't really mean very much when you're doing this. Well, this compound also, as I think, so Robinson had certain, he didn't. So the yield is uncertain and wasn't even optimized. I don't really see why I should waste his time optimizing it. Okay? Final comment. At Liverpool had to go to the bench and do it himself. He didn't have any students. So how would you guys feel like doing this yourselves? It's been a long time since I've seen a colleague. We all sit and think, and then we try to find students to do all the hard work. Right? Anyway, so Robinson had to do some work for himself. Well, that was just to get you to see where I'm trying to go. I want now to look at some basic aspects. There we are. Now, we have between methodology and synthesis. So what will happen a little bit is I'll go for one, and I'll jump to the other, and go back between methodology and synthesis. Okay? And the idea is that you will then understand a little bit more about what's happening. And the reasons here. Synthesis and organic synthesis are completely intertwined. You can't have one without the other. And have a look. A synthetic methodology only becomes relevant when somebody uses it in a synthesis. Now that's quite a surprise for many people who do methods. You do a method, uses it. And you say, why did I do that? The other, of course, the other way around is also true. You might need some good methodology. So you might have to, in fact, invent your methodology to do the synthesis. Well, with some basic concepts of organic synthesis. In the reactions and what I call, or we call, reaction hierarchy, which are the importance, which and what they're all. You should certainly think about making carbon-carbon bonds, single, double and triple. Each one creates a different problem, but we will be working on this now for so long. Making carbon heteroatom bonds are now much more important in this list because have oxygens and nitrogens. We've seen from the two colleagues who already they have oxygen atoms. Well, going down the list, functional group transformation. You don't get further forward, you don't build anything, but you do to adjust to do the next bond, carbon-carbon bond reaction. Oxidation and reduction, which is now being called recently redox. You adjust the redox level of your molecule to do the next reaction. But you're not going anywhere with these reactions. And of course, protection and deprotection, things you should avoid completely, because then you just don't go anywhere at all. You do the so that you can do another reaction. So we divide this scheme here. Very important, quite important, and as much as possible, because this will start. So Hendrickson, and he created an efficiency definition of synthesis, and this is definitely so important we cite it today. Many of us still cite the reference Jack's 1975. Efficiency of synthesis is the number of constructive reactions over the total number. Constructive reactions are reactions which will make carbon-carbon bonds and carbon heteroatom bonds, which you construct. We've looked at this for quite a while now, and you will be amazed to find very few syntheses will go over 70%. Many syntheses are about 30–40%. I will show synthesis by Corey if we get. I think it's about 5%. What does that mean? 5% of reactions are constructive. The other 95% of the reactions that Corey planned to make Tamiflu are not really constructive. There's only one reaction in the sequence of 10 or 11 reactions in which he makes carbon-carbon bonds, and it's the first reaction. So this can vary tremendously. What we would like, of course, is this efficiency getting to 100%. No time wasted in doing reactions which I'm not going to construct. Well, sorry about that. There we go. Well, I'm here, Vera Pardini, Hans Wirtler, perhaps some of you will know them from USP, and there is the famous man, Jim Hendrickson. I consider him to be one of the greatest organic chemists, perhaps not respected. He's written books on natural products. He's written the textbook with Crabbe and Hammond. He's invented SynGen, which was the first computer program to do retrosynthetic analysis. And he gave us the pleasure of his company in São Paulo and São Carlos. So here, that is the man here, that is Jim Hendrickson. So, now, this publication by Schwann and Chrisman, you can perhaps can see, I'm never too sure that at the back you can see all these details, but anyway, Samuel Daprave, okay, so it looks like we can see it. ChemStock reviews last year. Now what did Chrisman do, which I think can help us all? He found a way of using Hendrickson's ideas and making it more interesting to look at. So first of all, let's see what he does. He is transforming Hendrickson's ideas, the efficiency rule, into a more visual approach. So what do we do here? We have good reactions, green. We have going down the scale, not so good, not so good, till we get the point here. Reactions which you should avoid completely in your planning, in your synthesis. So we have an idea now. Good reactions, more or less, lousy reactions, please avoid them. So that we have this, and it's established here by the colours. I chose prostaglandins as the example. There we are, prostaglandins. I chose prostaglandins for the simple reason they were very, very, very important in the 60s and the 70s, and they got out of fashion. Organic molecules are fashionable at a certain time. If you look at the history of organic synthesis, who synthesizes steroids today? Well, one or two people do, but they just kind of get forgotten. Steroids are not fashionable. So we have molecules which are fashionable. Prostaglandins were out of fashion, they've just come back. They've just come back with a bang. Many people are looking at prostaglandin synthesis for the same reason. In the new directions, you must find new ways of making prostaglandins. So why would you want prostaglandins? Well, I do because I use it to treat glaucoma. So every day I have to put, so it's a prostaglandin that goes in there and controls my glaucoma. So many of you perhaps are using prostaglandins. Interesting point, Simon talked about Viagra, and if I get there I'll show you the Me Too, the other compounds. But there's a now. A new compound is a prostaglandin, and this will also supposedly help to cure erectile dysfunction. So we have those compounds that Simon showed you, and we also have now prostaglandin, which is on the market for this. So here we are with prostaglandin. This is the Corey synthesis. It's synthesis. And you can see now what we can look at. Two molecules are joined. The number in the ring is the number of atoms of carbon atoms. So you join 5 and 1, you now have 6 carbon atoms. The next step, of course, is to see 2 carbon atoms, and then you join 2 molecules, and you get 8. Then you have a string of reactions, you still maintain 8, and you join in 7, and now you've got 15 carbon atoms. So you can quickly see the number of carbon atoms which are coming into your synthesis. Okay? Here you can see this is what we call convergent, 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 and this of course is linear. And you can see all the steps, and at the bottom now there is a conclusion. You've got the so-called LLS, the linear sequence. 15 steps, and you have OY, the overall yield. They're just two criteria you could use to qualify syntheses. The overall yield for chlorine is 12%. But a quite long synthesis, and that is interesting still in industry to make prostaglandins. It's a good overall yield. And the compounds are fairly simple. Here's the molecule, so you can look at it. It's a 5-membered ring, 2 hydroxyls, and 2 long chains. It's called arachidonic acid. All these, and they usually have a couple of oxygens in the 5-membered ring. The latest synthesis, which I is by Agarwal from England. I will just mention there is a synthesis after Nicolau, about a year later. You should look at it. I've soundcast the 2 syntheses. The Nicolau is terribly poor in comparison to Agarwal. I would never have dreamed of publishing it after Agarwal had published his synthesis. But anyway, so the Agarwal synthesis, 2012. Here's the key reaction. Once again, succinyldialdehyde. Robinson used this. Oh, it's being used again. 2 molecules of this, and you've got a series of reactions. When was the aldol reaction invented? Anybody know? I don't. 18 something. So we're using reactions which are almost 200 years old, and they are key reactions still. So here we go. This is the key reaction. It's in using proline. It's an organocatalytic reaction, and the yield is lousy, 14. But look at what he's done at the beginning. From a simple molecule which you can easily make, he's created the basis of the. In fact, the thing is so good. There are 8 carbons. The thing is so good that 1 is actually too much. He's going to take this carbon off. In this aspect, this is anti-synthetic. He makes a molecule with 1 carbon which he doesn't want. So you have to take this carbon off in the synthesis. Here is the analysis. Here we go, 4 reactions to get this compound with 8. A bit of convergency, 8 plus 8 gives us 16. And then we have a small series of reactions, and then he joins in a 5 carbon compound. 5 and 15 gives us 20 of the prostaglandins. Linear, the LLS. 7 steps. So what he's done is to reduce the number of steps from 15, which was Corey's approach, and gone down to 7. Look at the overall yield. Maybe you can't see it so much, I'll just try and read it for you. 8%. It's actually lower than Corey's overall yield. But this has been taken care of about 2 years after. He published a further article, and he's now got the yield of this reaction from 14 to about 30. When it's 30, it becomes much more interesting by the simplicity of the reaction. Okay? So now we another aspect, and we'll see this. The old type of syntheses last century, you would never found out how much of the compound. You knew it was less than 1 milligram because they never showed it to you. You'll see that point later on. Here in the new syntheses, you tell us how much you made. 2 grams. Now that would make industry wild about 2 grams, but just incredible. Okay? So this is a approach for you to be able to analyze syntheses side by side. I suggest you read this article, it's really good. So, I won't waste much time on these things here. what are the major carbon-carbon bonds forming reactions? Well, I always say Diels-Alder because I've been doing this for a long time. I like Diels-Alder reactions, and fortunately Corey has suggested that the Diels-Alder reaction is still the most important reaction in organic chemistry. I'll try and explain that later on. So we've done this kind of thing here. This is things from our lab to make from two simple molecules a much more complex molecule. We'll talk about that in a short time. Well, I knew this was going to happen. One of my students called Andre, he does something funny with PowerPoint. I'm not sure what he does with PowerPoint, but you take his pictures and throw it somewhere else, it disappears. So yesterday afternoon, I put the image back in again here, the scheme, and I did this. You can see one has disappeared, unfortunately. What we were doing here are making spiral molecules using reclosing metathesis. And also, what Andre did was here. To make substrates for testing, we use cross-coupling reactions. What is the all of you should be thinking about using metathesis and cross-coupling in your chemistry, because these are two important reactions. And just to complete that, we should remember that metathesis and cross-coupling reactions are at least 50 or 60 years old. If you go back in history, you'll find that was doing metathesis, perhaps without even knowing about it. And cross-coupling began also, so these are reactions. Okay? Ah, wonderful, there it comes. So, now you can see the metathesis. We made these compounds quite simple, I'll show you later on a little bit. And we did the metathesis and closed the ring, made these spiral compounds. And in the same work by Andre, he also did the Sonneger-Scherer reaction, and we discovered things like metathesis, Diels-Alder, cross-couplings. They're very, very easy. Might now try oxidizing a secondary alcohol to find out how that is difficult. So we should not think about simple reactions being really simple and so-called complex reactions being complicated. It's the other way around. I've seen many syntheses stop because the person couldn't make an ester or hydrolyze an ester. Okay? So, going on now, synthesis. Let's talk about the reactions, a little bit of methodology, control, and efficiency. And I will repeat what Hans-Jürgen said yesterday. If you want to do a reaction, always prefer catalysis, because you need to think about using enantioselective catalysis. And if you start a mechanism course, you'll 90% of the reactions are actually catalyzed. Maybe a proton, maybe a base, maybe a compound, but most reactions are catalyzed, and you should prefer them for many reasons. Okay, let's go on. So, here we have Barry Trost, selectivity, chemo-regio state selectivity, and he also invented atom economy. And you've already heard about that yesterday. I would imagine and ask the question, is anybody here not chemo-selectivity? There's nothing you say you've never heard of it. If you've heard of this, I'll be happy in the sense I don't need to explain anything. So if you know about chemoselectivity, we can go on a little bit faster. So chemoselectivity is nothing new. Great. Well, let's get into the point now. Here it is, tactics and strategies. Tactics is the experimental part. How do you do the reactions which you've chosen to do? Strategies are about planning. So we think about tactics, we think about planning. Once again, methodology, organic synthesis, you can't separate them. You must have tactics in the lab, but you must have planning before you walk into the lab. Okay, that's the idea. A simple example. We like carbon. It's biomass. It's a simple molecule. And the best thing for me, it's free. I get it recently from Firmenich in Sao Paulo. So I get the compound for free. What have we shown with others is that you can do oxidation, oxidation, reduction, 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 and each kind of reaction is selective. Just the whole point is that, just to show some selective reactions. Carbon is a fantastic molecule. But I always knew I could react carbon in 8 of the 10 carbons. But I was wrong. You could do it 10 of the 10 carbons. You can react that the carbon I hadn't thought about was here, but somebody published that. The last publication last year, somebody has now managed to function methyl group. That is a really impressive reaction. So you can now do reactions on carbon and all the 10 carbons. Now if that's true for carbon, it's probably true for a whole lot of other molecules. When you do the deals all the reactions, we showed that when you do this isoprene, not isoprene, piperylene with thymoquinone, what we call the regio selectivity will put these two methyl groups together on the same side with this stereochemistry. If you want the opposite, this molecule, because this represents a group of homophyllenes. So what we did is to play around with the diene and change its electronic properties and therefore its molecular orbitals. So when it reacts now with thymoquinone, it does the opposite method. This is by the fact that this oxygen drives the regiochemistry of the reaction. So, we'll go on now to the new chemoselectivity, which we all have to learn about. It's already been mentioned, what we call CH activation and also carbon-carbon activation. Oxidation, putting in chlorines, etc. How do we do that? Here is the traditional approach. You get two compounds, both having, you get a compound having a functional group already present, and you just change it. Now, it just basically means you're doing SNU SNU2, and that's not really very creative. How about when you want to make the carbon-carbon bond? You get two compounds, but well, that is actually cross-coupled. So that's not really very new. What do we want? We want this, a carbon bond, one of carbon-hydrogen bond, and we want to change carbon-hydrogen bond and put in a functional group. That is the new approach, carbon activation. New, at least. Right. Here we have carbon-carbon bonds. We want to have has a carbon-hydrogen bond, and we're going to insert a carbon in this bond and make a new carbon-carbon bond. So these are the two objectives to get CH activation. Just a couple of comments. Late stage activation of the CH and CC bonds is very, very, very useful because you see the synthesis. You avoid deprotection, you avoid a series of consequences because you can put in the desired atom at the very end. And this has a second objective, which Hans-Jürgen mentioned yesterday. If you've got a molecule almost where you want it, from that molecule, if you can do CH activation, you can make hundreds, at least 10, 20 different molecules. And if industry likes this, they can start with a very, very advanced intermediate and make a lot of analogues from that intermediate without tremendously long syntheses individually to make the different compounds. Sorry about this. Probably by the end of how to use this thing correctly. Well, some of these possibilities aren't very interesting. You're not going to get famous realizing a carbon-carbon double bond, because it's been done for so long, there's not much novelty. You might find a new reaction. Allylic and benzylic. Usually allylic and benzylic oxidations. They've been known for 100 years at least, so not really great things to do. We have a group of reactions which activate molecules using what we call the directed group concept. I'll show you an example. We use our directed group in the molecule to direct the reagent to come in at a particular carbon-hydrogen bond. We'll not take too much. And these, of course, are of lesser importance. What we want is activation at a isolated, unactivated carbon-hydrogen bond. And that really would be great news. So there we go. Jumped again. Well, I'll give you, this publication came out very recently. You can see it's Angevin Chemie last year. The relevance, of course, is the major author, Hartwig, the Buchwald-Hartwig group who made the contribution to carbon-nitrogen cross-coupling, and he wrote this article. You can't really see very much, but the idea is, apart from a central steroid-type molecule, how can I react a compound which has at least or more bonds? But I want to do it selectively. I don't want to do just anywhere the molecule. So we have now lots and lots of reagents to do this. You can see the basic idea, and if you're in doubt, you can get a copy and look at the graphical abstract. The idea is to be able to do reactions selectively without any molecule. This is what we usually call substrate control. The molecule helps you to do reactions in a certain place. It's the molecule you are using which is directing the reactions. Now that's well done already. What we want is the opposite. We want the reagent to control the reaction. Now that is called reagent control on the substrate. The reagent decides where it wants to react and not the molecule. And that is the biggest lesson I like to teach. Our objective in organic chemistry today is that we decide where the molecule will react. We decide how it's going to react. If we let the molecule decide where to react, we're not really doing anything interesting. We have to decide how to react, where to react, and what are our objectives. And that is the thing that's been changing. We are now controlling reactivity molecules. Once upon a time, not so long ago, people just throw some reagents into a round bottle flask and see what it gave. And that's not. Sometimes it's like it was interesting, sometimes it explodes even. Now we have to do the opposite. Before we put anything into a round bottom flask, we must decide what we want the molecule to do and choose the right reagents, the right solvent, the right conditions. Okay? So, let's go. I'm not sure whether this is clearly visible. This is Christina White's chemistry, which is making a tremendous impact over the last 10, 15 years. What do we have here? We have a relatively simple terpene. It's actually readily available, it's quite cheap, and you can do two different reactions. If you can look at here, we have a lactone, so therefore we have a carbonyl group. On this side here we have an acid hydrogen. Take it off with LDA, put it in an oxidant, and you get hydroxylation at the side of the carbonyl group. Now that is part of the old chemistry, that's obvious. The question is how to do it, that's all. But you just use the enolate, and you can put in chlorine, oxygen, sulfur, anything. Now, that's one way. So what did Christina White do? This way. She used this reagent. It's an iron complex. The oxidants here, it's H2O2. The yield is very respectable, and this compound now oxidizes at this position in a very good yield. Now that is the reaction we're looking for. Doing an oxidant oxidation at a remote point selectively and in good yields, and also with a cheap metal, readily available metal. We've gone from let's see, I think it's molybdenum. We're now using iron, and iron will not be going into extinction in the next several thousand years, so we can count on iron. There's a second example here, which she did. She was trying to make things like artemisinin, which I would like to talk about in the second half. How do you make artemisinin? We'll continue what Simon said about malaria, so hopefully I'll get there. So what did she do here? Iron complex, iron complex. This is one, this is the other. You can oxidize this molecule using iron, and you can oxidize, or you can oxidize the side. The iron oxidants go to the same region of the molecule, but they attack in different carbons. So you've got selectivity, chemoselectivity. So that is really great for you to think about doing this kind of reaction. You can see the yields. I don't think we can compare when you are doing this kind of selective reaction. It's a good yield. Okay? Further examples. Now we're getting into the real idea, CH activation. So what she did and showed this is that we are now getting to the stage in these kind of CH activation reactions which to cytochrome P450 monoamines. Now that's the enzyme which knows how to oxidize molecules whenever it wants to. We have to imitate that, but we're getting there. So Christine is certainly getting there. So this slide, which is all part of the same publication, she has a list of the terpenes, steroids, alkaloids, peptides, amides, being oxidized chemically at CH bonds in a way which you at first sight would not expect. And the yields you can see 40, 50, 40, 60. I consider this to be excellent yields for this kind of selectivity in a very difficult reaction. Well, just there has been created in the States, funded by NSF, which is called CCHF. It's a center for functionalization of the CH bond. And the director is Hugh Davis. He's at Emory. We had him, and he is now. That's the group. You have to do this, but it's their funding. So this is the group of senior researchers who are taking part in this program. You can see that all over the States, but it's centered more or less in this part of the States, and they are looking at ways of doing CH and CC bonds functionalization. So it's a great incentive. So, just one final example, once again from Christina White, and you might want to look at this afterwards as well. She showed that in the syntheses which had on making not really erythromycin, but the precursor without the sugars. There is the molecule, partially complete. You can see the famous people who did syntheses before her. You start with Woodward, of course. You go through people like Stork. All the major, what we call, all the major in total synthesis are there. They all tried to make this molecule. And they did, because this is actually a list of publications. Okay? But they used a conformational trick to get there. As the molecule is acyclic, and you want to get the two ends together to react, you organize the molecule using cyclic components to bias. In other words, if you look at here, we have these two oxygens joined together, we have one or two other cyclic components, and they will get the molecule to have a certain conformation, and then it reacts to close the ring. She thought about this. What would it be like to do it without any biasic elements? Because that means cutting out reactions. It makes the so her idea is to simplify, taking out these biasing elements, these rings, and doing it straight on a acyclic molecule. Basically, the idea is to put in a carbon-hydrogen bond, put in a carbon-oxygen bond. In other words, you have an unactivated CH bond of this carbon, and you will stabilize from the carboxylic acid using oxidation. And the answer is yes, she did that. Okay? If you look at these things here, you can do this with no biasing elements. I would imagine this is not really clear at the back. I couldn't get the scheme to be further. But she has now managed to do this. Here's an example. Obviously get a bit of isomers. You get starting material back, and the yields are not, well, we have 70 here, but we have 36% here. The yields aren't fantastic yet, but they should get better as people work on these kind of reactions. And she's wrote a really good review, Jack's last year, where you can see all these examples and see where this kind of is going and where it's going. Many people are now looking at doing CH activation, late stage. Sorensen has published this on natural products, another one on natural products, and this is a chapter. And we know that the is doing work to try and get these reactions to get good yields. Of course, they don't really much, but now and then we find out something which is happening in the pharmaceutical industry. They are instead doing this late stage CH activation because they can make simple intermediates, and then from that compound you can make an array of different molecules by simple CH activations. So, I'm just going to mention these two concepts in synthesis. Atom economy, we've heard about that already, so it's nothing very new. The best comment I had about atom economy was from the pharmaceutical industry. They're not too bothered about atom economy, apart from the fact if you get all the atoms into the product, you've got much less waste to throw away, and that is good. So atom economy means actually less waste, and that is really important industrially. And the second one is Paul Wender, introduced molecular complexity increase, strategic efficiency increases if your molecule grows quickly. If you do an interesting reaction at the beginning, you get molecular complexity increase. So you get faster on the way to making your molecule. Once again, our deal's older. Yeah. Desapareceu. Okay. Just once again, a couple of examples from the lab. The point is here. Two simple achiral bonds do a Diels-Alder. You get a complex cycloadduct with carbon bonds and 4 new stereochemistries. Okay? The have so it's a great reaction. Think of any reaction you want to think about. Grignard. You will join together Grignard reagent with a carbonyl group. You're making one carbon bond. And I'm not sure how. 2 new stereochemistries. The Diels-Alder is a double of that. You make 2 new bonds and 4 stereocenters simultaneously. Okay? Well, what we're going to do now, the next few minutes, talk about retrosynthetic analysis by way of disconnections, and I will try to tell what has changed since the last century coming into this century. Okay? This is obvious. First of all, you never get to invent a new wheel. It's been done a long time ago, so do not try to invent a new wheel. Okay? Secondly, this gentleman here, who was around 2,500 years ago, had already pointed the way to us. There is strategy without tactics is the slowest route to victory. Tactics without strategy, you're certainly going to get defeated. You have to have both of them. And this has been known for 2,500 years. Okay, so the gentleman was more interested in wars. But the idea in C, I think, is quite a... Okay. We're going to talk about a little bit about retrosynthetic analysis, which is to Corey. Carbon-carbon bond disconnection, which I would like to put to Stuart Warren. And of course, we've just mentioned molecular complexity increase, Paul Wedder, the ideal synthesis concept. We're going to see this a little bit later on. So here, just to remind you, Stuart Warren, Cambridge. Here's the first book. This is the first edition. It was published, I think, in 1980. And he was the person that brought to us an understanding of what is disconnection. And we use this book as a textbook. There's a second edition come out right now. Another thing he does is this comment here. I'm sure you can understand what's written there. That's what we all say. I'm teaching organic chemistry. It's very, very easy. You're trying to learn. It's very, very difficult. Right? So the man said this. He actually wrote it. It's in the foreword in this book. He's had a few other comments. Other comments I'm going to waste a minute and say is this. He taught us. The students say, I understand everything you say in your lectures. I just can't do the exams. I think it's nice comments from the same man. Okay? Well, synthetic efficiency and strategic efficiency will depend on these criteria. The total step number count, the overall yield, the longest linear sequence, convergency, which will we still love the linear route, okay? But we have things like time, costs, availability of starting materials and reagents. And this affects us as well as it affects, Hans-Jürgen told us yesterday about the pharma industry. But it's also the same thing for us. We have to worry about the synthetic operations, as was mentioned yesterday. If you go into an ordinary lab, you can't do any reaction you feel like doing. You don't have the conditions. So we have to think about that. the conditions themselves, how to do analyses, and you will all. The reaction is very easy. The very time consuming and frequently not very successful. So you have to plan the reaction, the extraction, and then the purification. Okay? Logistics. This is by Johann Mulzer, which he showed basically that as the number of steps goes up and the yields are in each case 70, 70, 70, which is a good average. You could try for 80, we'll see that. 70, 70. After 20 steps, which you have a of 0.08%. In other words, if you you can more or less the comp, but not much of it. We have here the number of steps, 5, 10 is now a good average, 20 is the limit. When you get 90s, 80s, 70s, you can see how the yields go down. And this is obviously very important in any kind of synthesis, because it's not just the industry that needs product to sell. You need the product for some reason, and you have to have the product to keep on going with your research, whatever purpose. So, we'll look at these things. I call them philosophies. Maybe they're not. So we have basically these philosophies. Target-oriented synthesis. The old-fashioned we meant to make a molecule, one. So we look at this target. I'd put a name, Woodward, you could function-oriented synthesis. Paul Wender, we call it FOSS. Diversity-oriented synthesis from Schreiber, we call it DOS. And Danishevsky has a variation, which I won't mention because it's just on FOSS in DOS, and the eventual target. We also have lead-oriented, we have all these things here which use to direct your interest. So that is oriented synthesis. You are here, and there's the target. And you have to hit the target. If you hit at the side and don't get the target, you don't publish. You can't. I almost synthesized the molecule, but I synthesized something else. So it's time to go back and finish off the synthesis first before you try publishing, which you didn't do. FOSS. Here's a molecule which is quite interesting for its biological. And you can see in the colors which are the as far as biological activity is concerned. So what Paul shows us, you can get the same kind of points with simple molecules. Even more simple. A simple, you can put functions around the benzene ring and you should get the same activity. Okay? And this actually works. The idea at least. You go from the complex, which you can't synthesize, to the simple, which you can make very easily. That's the idea. Here we go. Bryostatins and bryologs. Here is the bryostatins. You can see here. Molecule, which means when you get there, you've got nothing to show anybody. You've got a little bit of a smudge in the round bottom flask. Well, actually, Paul has got this number down to 30 in a recent synthesis. But when he did this, here are the bryologs. You take out a lot of the molecule, which is not used, and you can use and find this molecule. Look at that. 1 0.3, it's actually more active than the natural product. So it's a simple, you can make it more easily, and it's actually more active. So this is a great idea, at least as far as I'm concerned, for making what he calls biologs based on biostatins. Well, I'm just looking at the time. Just go on a few minutes. There we have diversity-oriented synthesis, created basically by Stuart Schreiber. The first publication, I think, was in 2000. He got together with Martin Burke, who was his postdoc, and they published a second review in 2004. These are actually fantastic. What's the idea? When you look at this, it's the opposite of retrosynthetic analysis. You start from one compound and you spread out to make a lot of compounds possible. You start with A. Using different reactions, you can get different molecules. Simple reactions. From each of these, you can do once again the same reactions and get new molecules. You are increasing complexity, you are constructing molecules, but in an organized way. This kind of chemistry is being used. Some people have got round to making 1,000 or more molecules based on this principle. So your chances of finding a molecule with some kind of interesting activity, bio, anything like that, the chances go up tremendously from that point. So Stuart Schreiber was proposed. Well, I'll let this thing go on. There we go. I'll let it finish. What we did, we started with a simple. We could use carbon, I've mentioned before, do some kind of target-oriented synthesis to make this cycloheptanone, which of course is not natural. And the idea is this carbon here, and we can do a whole series of different reactions, quite simple reactions. They're all mentioned here: metathesis, ring-closing metathesis. We could use the Wacker oxidation, and so we could make a series of compounds. Even this molecule was made. It's an alkaloid sesquiterpene. We can make 7,5 ring systems. We can make this ketal, which I don't know how it's done. I haven't the faintest idea what the mechanism is. And we've made all these kind of compounds. We've even done a 2+2 cycloaddition to get benzenes. And of course, the interesting thing about these benzenes is that to get compounds is not easy. And once again, it seems that the pharma industry likes these kind of molecules. So maybe this could be interesting. Okay. Well, here he is. Just there is the great master, Woodward. He didn't really live as he should have done, but you can see one of the reasons why he didn't live that long. He was found smoking all day long, usually with a big bottle of whiskey at the side to make the day go better. So he did that. Anyway, here's the comment. So you made a natural product. Try doing that without NMR, because he did. When he started doing natural products, he did these without NMR. He actually did some things using ultraviolet only, ultraviolet spectrum. Anyway, here are the things. Woodward-Fieser, the rules about ultraviolet spectra. Woodward-Hoffmann rules. There we have the great syntheses. He worked on with orbitals, mechanisms, and he had a unique knowledge of the organic chemistry at that time. On the other hand, he never explained to anybody how he did syntheses. So we shall never know now how he planned these syntheses. What we can learn from the things is just looking at the beauty and the efficiency and the genius of this man. Two statements from him. There is excitement, adventure, and challenge, and there can be great art in total synthesis. Okay, published in '56. And this is for the students, something we always say. There is absolutely no reason or explanation for you not to do the reaction. Because if you don't do the reaction, you will never know the result. And so you can't tell me, the reaction doesn't work, you haven't done it. So you have to do the reaction. It's the first thing. Woodward said this, perhaps before me, but I've been saying it for a long time as well, that we should have this kind of rule. Never tell anybody, this reaction won't work, I won't do it. You've just lost the Nobel Prize, because that reaction would have worked and given you a Nobel Prize. Okay, we're getting there. There's a big problem. Organic synthesis has become, for many people, too important. We get too much money. It sounds silly. We'll talk about that. We don't get all that much money. So here's a good example of when you start to get famous, very rich, you start to get criticized. Nobody criticized this man here 50 years ago, but we are now criticizing every day that he's now talking on television about soccer. Okay, here we start. The Trouble with Synthesis, written by John Cornforth, 93. I think perhaps he was the first person to talk about this. And the interesting thing is, his Nobel Prize is really organic synthesis. But he did it for a very special reason. He wanted to investigate the biosynthesis of terpenes. So he made molecules to use in his studies. And this article by Cornforth, there are things by Heathcock, many things by Whitesides, Sabak, and if you start looking at blogs and other, you will find that we are getting more and more criticized, sometimes violently, by people. Okay? We'll have a little bit look at this. The big question started is, this kind of academic work, it costs a lot of money. And it costs a lot of people. It costs them money, and it costs you as well. You're going to get trained in this. Okay? Synthesis. Big question. New knowledge. Do we really get new knowledge out of these great old-fashioned syntheses? And what has society got back in return? Okay? These are the basic questions. Well, most of you should find out about Thomas Hudlicki. He is my guru. What he says, I take seriously. And this is one of Thomas's standard jokes. You've heard about the emperor's new clothes. His tailor gave him some new clothes for him to walk around in the center. I would think Jean-Pierre would be in Paris, wouldn't it? Anyway, the clothes are wonderful. There's nothing there. He went out nude. But everybody had to say, the emperor's new clothes are wonderful. The same thing is true in organic chemistry. Here we have somebody saying, that's a great yield, professor. And somebody looks at the little kid looks at the flask. And he said, there's nothing there. It's a great yield, but there's nothing there in the flask. The quiet reply, shut up. Because the emperor is right there. Okay? So this is the kind of thing about what is happening within this kind of topic. I'm going to finish in about the last 5 minutes for a coffee break. Let's look at I think this we can call the last big monster synthesis, never to be repeated again, probably. We'll see. It was done by the Kishi Group, publications round about 1980s. How big? How big is the group? Well, it's interesting here. The synthesis actually wasn't really published, all of it. It's just so long. Phil Barron made an estimate that the synthesis goes over 170 steps. 170 steps. So we have a clear idea the yield must have been really, really low. And there wouldn't be much material produced. So here is parathoxin. This group last century. And this is the statement here. If you get a very large NSF grant, well over and you have at least 20 to 30 brilliant postdocs, the lab can synthesize even the want to make you can make for good or for bad. And usually these kind of syntheses take to years to complete. So did his work, he thinks now, well, the publication will come out in 20 years. The first. Now, we can publish things about the root, but people that are at the beginning of the synthesis, it's a long wait. So, for example, this is my talk, and this is the gentleman, I call him so we write KCN, and this synthesis has not been accomplished yet. Well, we all in Brazil know what this little animal here, and we know what this thing is here. To catch Nicola. He certainly won't complete the synthesis because simply he can't get the money and he can't get the students anymore to work on this monster synthesis. So this is the last synthesis that won't happen. Okay? Well, what we have to criticize in these syntheses, this is the big science question. You have to reply to this question in what you're doing. Well, what do I know now when I finished that I did not know when I started? That's the big question. If you don't know anything new at the end, your research is really worth very much. You have to discover something during the research. It says, now I know this, this, and this, which I did not know before. Okay? What happens in these big syntheses, if you look at them with certain care, the molecules are so big. Usually they start off with a great retrosynthetic analysis plan. We're going to get the parts together quickly in maybe 5, 10 reactions. And then something goes wrong. The subsequent reactions don't work as they should do. And they start to get worried about the big question. If you're doing syntheses at this level, you have to publish first. You can't be second, because nobody remembers who came in second place. You only remember who came in first place, first. So you have to do this. And you start to get worried, and you start to rush, and you stop being original, and you stop creating, and you stop learning anything new when you do all this. Okay? Now that is the big criticism about these monster syntheses. They get to a point where there's a big rush to finish and publish. Okay? I'm almost there. What happened in the 60s, that both American and some European funding agencies decided that what we used to be called physical organic chemistry, mechanisms, was less important than synthesis. So they took money away from one topic and gave this money to synthesis in the 60s. Okay? So here's the surprise. They also observed the same things. Organic synthesis is just making monster molecules. It's a waste of time. It's a waste of money. So we do what? The money goes down to catalysis. And I would personally agree. You have to stop these monster syntheses. It's a personal opinion. And go to simple synthesis, which I'll try and show you. And then we'll perhaps get some money back from catalysis. Probably not. Okay? So after coffee, maybe we can get here at 11 o'clock. The reason is simple. I must really stop at midday I will be taking Simon to the airport as soon as we finish. So please, 11 o'clock here, so I can finish at midday. Okay?